rates problems that we're gonna do today are simple problems. They're problems where everything works out nice and perfectly for you, and there's no issues, there's no like multiple equations that I have to do, except on your homework, there is one problem like that. But it's gonna be like a challenge problem to see what you guys got. Okay? But it is pretty easy. It's just a matter of getting used to how to work out the problems, how to set them up. And I have this really cool thing to help you set them up that'll make your life so much easier. It's called Fuigi. Have you ever heard of Fuigi? Have you ever gotten Fuigi with it? Oh, it's Jiggy? Oh, okay. Well, in calculus we call it Fuigi. We're gonna get Fuigi with it. No. Okay. Got it? We'll put this on later, okay?
That's a county in Nigeria.
Alright, so let's see. It says, what comes to your mind when reading the following? Right? So every time you read a related rates problem, there's going to be some words in it, and you have to put it together, alright? So read this and tell me what comes to your mind. A ladder is leaning on a building and begins to slide down. So you should be thinking of a picture automatically, right? So that's the first thing you do is, what does this picture, what would it look like if I were to draw it? Like a right triangle, right? So we have some building, and we have a ladder leaning against it to the top, and then we have the ground, right? Yes? Okay, so awesome. So on these particular problems, sometimes it helps us to draw a picture. So if you need that, then you draw the picture. If you don't, then don't draw it. Okay, Axel?
Yes.
Alright, so the next thing to ask yourself is what's changing? So if I had this picture and it says that the ladder begins to slide down, what would be changing? We kind of talked about this on Friday. The angles? Okay, so like this angle right here would be changing. Okay, so angles are changing. Not all of them, right? Just this one and this one up here? Okay. The 90 would stay 90 all the time, right? Would this one be getting bigger or smaller?
Smaller.
Smaller? How about this one? Would this one be getting bigger or smaller?
Bigger.
As it went down. Bigger? Okay, cool. If this one gets smaller, then the other one has to get what? Bigger, because they have to end up balancing out and equal how much? 180, right? Very good. Okay, what else is changing? The distance from what? The building to the base of the ladder? Okay, what else is changing? Somebody said the height. So this height is going to be changing. Is the height increasing or decreasing? It's decreasing, right? Anything else? The area, right? Very good. The area would be changing. Is that about it? Base of ladder, right? So the distance from the building to the base of ladder. I just didn't put the word the. Calm down. Oh, I'm sorry.
I'm not the problem.
Good? Alright. What equations can you think of that would help me to solve for any of those things? Pythagorean theorem comes to mind? Okay. So a squared plus b squared equals c squared. So a lot of the times when we're dealing with a triangular shape like this, we're going to use Pythagorean theorem. Especially when we talk about ladder problems or shadow problems. Any problem that involves a right triangle. Right? If we were talking about the rate at which the area changed, then I wouldn't need Pythagorean theorem. I would need what formula? I would need the area formula, right? Of a triangle, which is 1/2 base times height. If I were talking about the rate at which the angles were changing, then I wouldn't need this formula nor that formula. I would need something involving what? Sine, cosine, and tangent. Do you remember SOHCAHTOA? SOHCAHTOA! Yes? From geometry, remember Miss Unia? Okay.
When I hear that name, it's
So
just like...
SOHCAHTOA. Good? So remember that, okay? Awesome. So those are the things that should be going through your mind when you're setting up these problems, okay? Good? Alright.
Oofa.
There's a couple of things that you have to think about when you're trying to set them up. So as you're reading them, these are some things to pay attention to. Right? This is the Fuigi that I was talking about. F, W, G, E. So first down you write an F, and you want to ask yourself as you read that problem, what is it that I'm trying to what? Find. The second thing you write a W, and you say, okay, when? Okay? Usually it says the word, it'll say find this when this equals that. So it's kind of like obvious, right? It's telling you find this, oh that's what I'm finding. When? Oh, when this equals this, right? So it's usually pretty straightforward. You can fill up the find and the when really easily. Then given, oh my god, well, what are they giving me, right? And the last thing is you need to find an equation or several equations that relate to the variables that you're working with or you're trying to solve for. Okay? Sounds good? So what does the F stand for?
Find.
Find. The G?
When.
The G? Given. The W?
When.
And the E? Equation. Good. Don't be a robot, okay? Awesome. So let's look at this problem and let's see if we can find the Fuigi. See if we can fill in the F, the W, the G, and the E. Alright, here we go. A pebble is dropped into a calm pond. So if I drop a pebble into the pond, what happens as the pebble falls? It forms a ripple, right? A little circle, right? And that circle just keeps what?
Expanding.
Bigger and bigger and expanding, okay? So, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, so what is it that we're trying to find? Usually that comes out in the question part of it, so in the last section. We're trying to find the rate of the area of the water, right? So we're trying to find the rate at which the area of that water is changing. What shape is that circle going to be? A concentric circle, so basically just a what? A circle. So if I'm trying to find a rate, that means I'm looking for a what?
Derivative.
A derivative. So what notation would I use to denote that?
dy.
Not dy. Why dABT?
The area.
Because it's the rate of change of the area. Okay, I'm not going to put y unless you're describing y to be the area, right?
Yeah.
Let's use a letter that correlates to the problem. Okay, when? Look, it even says the word when. When? The radius is 4 feet, right? So what's the when? R equals 4 feet. And write down the units as you write down your information so that way you know that everything's in the correct units. Sometimes they give you feet here and over here they give you inches. So then you're like, oh no, I have to make sure that my units match. So be very careful, okay? Given, what are they giving us? The 1 feet per second, what does that stand for? The radius r of the outer ripple is increasing at a constant rate of 1 feet per second. What does that mean? Is that a rate or is that just r? It's the rate of change of r, so that should be a derivative. So what am I going to use to denote that? dr dt equals 1 foot per second. Are we okay? And what should be the equation?
The area of the circle.
The area of a circle. Very good. Okay, how do I know to use the area of a circle?
Because it's asking you for the total area of the.
Because it's asking for the rate of change of the area, right? So what's the formula for area of a circle?
Pi r squared.
Pi r squared. How am I going to get dA dt? What would I have to do to this? Right, I would have to find its derivative, right? So what's the derivative of A? dA dt equals, what's the derivative of this over here? 2 pi r times dr dt. Right, take the derivative of it normally times the derivative of the variable. Is that on our notes from Friday? Yes, okay, so if you're not sure, you can find it there, but if not, you need to be able to figure it out either way, because you're not going to have those notes on the day of the test, right? So practice finding it every single time you have to use it, so that way you don't depend on just being like, oh, it's going to be there, because it's not going to be there. Okay, so now at the very end, after I differentiated, now I can substitute things that I know. So do I know what r is? Yes, it's 4. Do I know what dr dt is? Yes, I know it's 1, and that's going to leave me with this guy, which is what I'm trying to find. So super easy. dA dt is equal to 2 times pi times what? 4 times 1. And let's leave it in terms of pi because we don't have a calculator. So this will end up being what? 8 pi. And what are my units? Feet squared per second. How did I know it had to be squared? Because it's area. Very good. Got it? Did that Twiggy make it a little bit easier to work through? Yes. So remember, okay? Don't get jiggy with it, get twiggy with it. Ready, Anias? Let's try the next one. Read it for us, Anias.
Cubic centimeters per minute. How fast is the radius of the balloon changing? The radius is 30.
So that's kind of like the example I gave you on Friday when I filled up the balloon, right? Okay, so what is it that they want us to find? How fast is the radius changing? So is that a rate? Yeah, so what would I use to denote that? dr dt, that's what I want. When? Oh, they didn't say when this time. What did they say this time? At the instant, the radius is 30 centimeters. So we know that r has to equal 30 centimeters. Okay. Given, what are they giving us? 800 cubic centimeters per minute. What does that represent? What rate does that represent? The volume, right? The rate of change of the volume, right? Because it's being inflated. So that would be d what? dV dt equals 800 centimeters cubed per minute. You know it's a rate because of just the units, right? Just the way the units are written, you know it has to be some derivative, some rate of change. Okay? Alright, what equation would I end up using for this problem? What shape are we talking about?
Sphere.
A spherical balloon. So we need the what of a sphere? The volume. And what's the volume of a sphere formula? 4/3 pi r cubed. Okay, we've got to get units cubed, right? So we've got to multiply 3 dimensions. Good? Alright, so what do I have to do to it now to get it to end up with a dr dt? I have to find its derivative, right? So that would be dV dt equals this times this, the 3's cancel out, so we get 4 pi r squared, because we take away 1, times dr dt. Okay, what is it that I know for this problem? I know r, right? 30. I also know dV dt, so that only leaves me what? dr dt, which is one variable, which is what I can solve for because I only have one equation. Right, so let's plug in what we know and solve. We don't plug in till the end, okay? So we would end up with 800, right? equals 4 times pi times 30 squared times dr dt. And now let's simplify. So what's 30 times 30? 900. 900 times 4? 3600, right? Okay, so we have 800 equals 3600 pi times dr dt. And now how can I get the dr dt by itself? Divide, right, by the 3600 pi? So we can cancel out these zeros and just think of it as being 8 over 36. And is there something that goes into 8 and also into 36? 4. How many 4s go into 8? So 2 over 9 pi. And that's equal to dr dt. And what would be the units? Because I always need to put my units. Centimeters? Cube? Per minute? Why is it not cube? This is just radius, right? And the radius is centimeters. So the rate of change of the radius would be centimeters per minute. It's not area, it's not squared, it's not volume, so it's not